せん。すいません。
So I think it's pretty cool. I don't have personal experience with it. Hardware, mobile,
is the next thing to cover. So the problems when it comes to deploying on something other than like a nice machine is that maybe it doesn't have enough memory, or maybe it has a low power processor, so it's actually very slow. Or maybe it'll eat up your battery, so it's kind of like expensive to compute on this device. So often what people do is they reduce the network size, or use some kind of tricks, or potentially quantize the weight to deal with these problems. And just in terms of like nuts and bolts, there are mobile versions of frameworks like TensorFlow Mobile and TensorFlow Lite, but the problem you might face is that they have less features than full TensorFlow. And so you potentially have to adjust your network architecture to make it work with the mobile version. So the first thing I want to talk about is just methods for compression of networks. So the idea that you might have is like, well, I've trained a network with 1 million parameters, but do I actually need that 1 million of parameters to serve predictions? The answer is often no. You just need some subset of the parameters, and there's methods for doing that. So you can remove correlated weights. You can add certain sparsity constraints in the training, such that less things are kind of used, even though like they could be used, but the network is incentivized not to use them as it learns. You can introduce cool structured computational filters that make them a lot lighter weight, and that's coming up on the next slide. You can also do something called knowledge distillation, which essentially means you train a deep network on your data, and then you train a shallow network on the predictions of the deep network. So essentially, like the data has a certain complicated, data distribution manifold that a deep network is better able to infer and kind of match itself to it. But as we saw in Peter's lecture on Friday, for those of you who were there, you can represent any function at all in just a one-layer network, one layer, such a way to go. So there is a shallow network possibility that's able to represent any network that you trained using something, and then if you can make it work on TensorRT, then it can be optimized for NVIDIA embedded devices. So the other big thing in I guess deploying embedded devices is reduced precision computation. So I talked briefly yesterday about float 16 versus float 32. So basically, the idea is that if you can train your network using float 16 instead of float 32, 16-bit precision, floating point numbers versus 32-bit precision, then it'll probably work just as well, but it'll use way less memory and be faster for that reason. And GPUs today, like the new Turing architecture, is really aimed at supporting that 16-bit computation. For the embedded device, it's also super nice because it just uses less memory, and so bigger networks can fit onto the same device if it's in 16-bit versus 32-bit. So I don't have much to say about embedded devices. I don't have personal experience, unfortunately. I know some of you have deployment targets that are embedded, and I think the Slack is a great place to trade notes about what worked for you and what didn't, and I'd be interested and curious to hear as well. Yeah.
Can you just elaborate on what you mean by your network will work on TensorRT?
I probably actually cannot elaborate too much on it. Well, yeah, sorry.
Can you talk about, are there any pros and cons to the reduced precision?
So let's forget about embedded, and let's say you're just training stuff you're going to run stuff on your own PC or deploy it as a web thing. So should you be doing training in 32-bit or 16-bit precision? So it's almost, so there's a blog post that I've seen that even talks about 8-bit precision, and the idea is that you can almost think, so let's think about dropout. So dropout randomly turns off some of the weights or sets them to 0, and then the idea is that the network still works even though every time computation goes through it, it uses a slightly different path, and then it essentially injects the noise into the system. But it might actually be helpful because the network learns to deal with it, right? And so this blog post was making the analogy to reduced precision computation, where is the difference between 0.0001 and 0.0001. Like, if you start kind of dropping precision, your network can still learn, even despite the noise that's introduced by things getting disrupted correctly. And it's just an empirical, like, I don't think there's theory that's good behind it, but empirically, it seems like you can reduce precision and still have networks that train correctly. The big con is that the gradients are sometimes incorrectly clipped then. And so I think a common trick is to do this gradient scaling. When you do reduced precision training, you essentially multiply every gradient by like 1,000 before you compute, you multiply your stuff by 1,000 before you compute the gradient, and then you divide it by 1,000 again and pass it on down into the other layers. So it's almost like when you do computation, you scale out the precision, and then when you don't need to do computation, you scale it back down. So that's the one thing to watch out for. But basically, I think the advice is, like, if you can make 16-bit work, then you should probably use it. It probably will be better because you can push bigger networks through. So I guess I want to go into the labs. Yep.
Yeah, about 2 weeks ago, we announced something called Loopy. Where that one comes in, and they say that code-free deep learning that can handle like lots of input images such as text, speeches, speech, everything.
I haven't heard of it yet, so I'm not sure. The question was, Uber released something called yes, or 2 weeks ago. I haven't heard of it. Yep. Oh, interesting. So the question is, are there licensing concerns when you're using certain data sets and then actually deploying your trained model? So the common concern that people had when the deep learning revolution was kicking off is, like, ImageNet has a license that forbids commercial use, and ImageNet was obviously the thing that everyone was training on, and then fine-tuning on their data a tiny bit. And so the question was, is it legally kosher to train on ImageNet and then release that network for